Most professionals attempt to navigate complex environments using an outdated cognitive operating system. We are naturally wired for deterministic thinking. We expect that if we execute action X, result Y will happen. But reality is a complex system driven by variance. A single action does not guarantee a single outcome. It initiates a spectrum of possibilities. Doing X might mean there is a 70% chance of your target outcome, a 20% chance of an alternate reality, and a 10% chance of a complete anomaly. Adopting a probabilistic mindset shifts how you view the world. You stop seeking impossible guarantees and start focusing on making high-quality bets. Letting go of the comfort of certainty is the mandatory first step to accurately mapping risk and surviving in high-stakes environments. The foundation of this mindset requires breaking a deep psychological habit. You have to decouple the quality of your decision from its immediate outcome. This matrix maps how decisions and outcomes actually interact. We evaluate choices on one axis and the results on the other, revealing 4 possible states of reality. A perfectly logical decision can still yield a bad outcome. That is bad luck. Conversely, a terrible decision can yield a great result. That is dumb luck. If you judge your strategy solely by the result, you will abandon a mathematically sound process just because you hit a localized pocket of bad variance. This framework eliminates the search for a flawless solution that works every time. The objective becomes finding interventions that shift the odds in your favor by 5 or 10%, edges that compound over a long enough timeline. When you define the mathematical likelihood of failure up front, a sudden bad outcome stops being a devastating surprise. You expected it to happen a certain percentage of the time, and today simply fell into that bucket. To measure those compounding edges, we rely on expected value, the mathematical engine that determines the true worth of any strategic bet. This equation calculates the anticipated average outcome of a decision if you were to repeat it infinitely. Consider a bet that costs you $100. You have a 20% chance of winning $1,000 and an 80% chance of losing your entire investment. Most people would reject those odds. But when you resolve the equation, the mathematical value of that bet is positive $120. If you execute this bet 10 times, you will lose your investment 8 times out of 10, but the 2 wins generate $2,000, easily absorbing the losses and pulling your net trend line sharply up. This creates a severe psychological paradox. To follow the math, you have to execute a bet that will make you look like a failure 80% of the time. Professionals cultivate the discipline to execute positive expected value bets, regardless of the short-term optics. The problem is that our biology actively fights this discipline. Human brains optimize for dramatic stories and emotional reactions, not cold statistics. To override this biology, we can look to theoretical physicist Richard Feynman, who developed a method for internalizing highly unintuitive systems. The technique requires you to take a blank piece of paper and force yourself to explain a complex concept using language a child could understand. When you strip away the statistical jargon and write out a concept like expected value, you immediately expose exactly where your intuition breaks down. Writing out these mechanics creates a mental friction that forces you to acknowledge the math, providing a necessary check against our narrative-driven instincts before you move to the final 2 pillars. The second pillar relies on base rates. This is the general likelihood of an event happening before you introduce any specific details. This grid represents 10,000 people. Let's assume one person in this population has a specific rare disease. The base rate is 1 in 10,000. Now, imagine taking a medical test for this disease that is 99% accurate and getting a positive result. Panic is the immediate human response. But watch what happens when we run a 99% accurate test across the entire population. It accurately flags the one sick person, but its 1% error rate also flags roughly 100 perfectly healthy people. Look closely at the comparison. If you receive a positive result, you are just one dot in a pool of over 100 flagged results. Assuming you have a 99% chance of being sick is a cognitive error called base rate neglect. Because the starting population is so massive, the false positives completely drown out the true positive. Your actual chance of being sick is still less than 1%. New evidence feels dramatic, but if you fail to anchor it to historical baseline probabilities, your conclusions will be mathematically useless. To safely process that new evidence, we use the third pillar, Bayesian updating. This is the formalized process for changing your mind as reality presents new information. This diagram visualizes Bayes' theorem. It requires three elements: your starting point, known as the prior, the new information, known as the evidence, and your updated belief, the posterior. Imagine a smoke alarm goes off in your house on a Tuesday. First, we establish the prior. The base rate probability of your house catching fire is incredibly close to 0. Next, we evaluate the evidence, the screeching alarm. A real fire triggers it, but the context is that burnt toast, high humidity, or a dying battery trigger it just as effectively. Because the starting probability of a real fire is so low, the new evidence doesn't jump your belief to 100% certainty. It merely shifts your posterior belief to a 5% chance of fire and a 95% chance of a burnt bagel. The Bayesian framework scales your beliefs proportionally, nudging them based on the weight of the evidence, rather than allowing a single data point to override everything. By formally balancing new information against historical baselines, you are mathematically protected from overreacting to alarming headlines or clinging stubbornly to outdated assumptions. You cannot build a probabilistic mindset by treating these concepts as an a la carte menu. They must integrate to form a functional strategic engine. Here is the complete architecture in motion. Base rates provide your starting prior. Expected value dictates your bets. And as reality plays out, Bayesian updating feeds new evidence back into the system to refine the next decision. This loop creates a strict operational rule. Strong beliefs require overwhelming evidence to change, while weak beliefs must be updated constantly. We live in interconnected, volatile environments, and we will never be able to tame or control the variance inherent in them. But while the final outcomes remain out of our hands, adopting these mathematical models gives us control over the quality of the bets we place.